Each of the chemical elements that are the building blocks of the Earth has its own unique physical and chemical properties. But there are certain patterns to these properties and a remarkable way of organizing these patterns. Hydrogen and oxygen are in the clouds, nitrogen in the wind, calcium in the rocks and in the river water that washes over them, magnesium in the chlorophyll of a leaf, carbon in the tissues of a crayfish, and copper in its blood. One simple compound of iron and oxygen in the rust of a nail, and over 1 million complex compounds in the chemistry of a grasshopper. The elements and substances they form are the materials out of which our world is made. The landscapes of our world vary considerably, but with maps, we can organize many different kinds of geographic information. The elements that form our world vary too, in their physical and chemical properties. But only one map is needed to organize the vast amount of information we know about the elements. This map is the periodic table. In many ways, the periodic table, like a map, can help us organize our knowledge of a diverse world, the diverse world of chemistry. How does a map organize information about an area? One way is to classify differences in the regions. For instance, a map might show by its colors and symbols that land is here and water is here, and a marshy area separates the two. This is a very broad organization of information. Information about the elements in the periodic table is broadly organized in a similar way, dividing the elements by their properties into regions of metals and metalloids and nonmetals. A map can also organize information according to similarities within a given area. A contour map, for instance, can organize information about a land area on the basis of elevation, or about a water area on the basis of depth. The periodic table also organizes detailed information. The elements are arranged in order of atomic number, the number of protons in a nucleus. Each row across, or period, shows one kind of relationship. Each column down, or group, shows another. The detailed relationships that the periodic table shows have made it probably the most important organizing instrument of chemistry. Let's see what sort of information we can get from it, and, more important, why it works. In the metals section of the table is lithium, element number 3. Because it's a metal, we would expect it to conduct electricity well, and it does. Beryllium is a metal too, but to the right in the table. Beryllium conducts, but not as well as lithium. And boron, to the right of beryllium, is a poor conductor. So these 3 elements, in this order, show a downward trend in conductivity. If we tested them for a certain kind of chemical reaction, we'd find a different sort of trend. For instance, suppose we allowed them to react with a hydrochloric acid solution. Lithium reacts vigorously. When all the hydrochloric acid is reacted, and we allow the liquid to evaporate, the solid that remains is lithium chloride, LiCl. There is 1 chlorine atom for each lithium atom. Compare these properties to those of beryllium. It reacts more slowly with hydrochloric acid. It forms BeCl2, 2 chlorine atoms for each beryllium. Boron reacts very slowly and forms BCl3, 1 boron atom, 3 chlorine atoms. So now we have also found a downward trend in reaction rate and an upward trend in the ability to bond with chlorine. Similar upward and downward trends in many properties of the elements are repeated throughout the entire table. For instance, take melting point. And let's start with element number 1, hydrogen this time. Hydrogen's melting point is low, but helium's is even lower. Now, from lithium to carbon, melting point rises. Then it suddenly drops and reaches a low point at neon. And with sodium, starts up again to silicon. Then drops to a low at argon. Then starts up again at potassium. Now it's clear that there's more than just a trend up or down. There's a pattern. And if we graph the melting points of all the elements in order, period by period, then the repeating or periodic nature of the pattern shows itself. Each repetition or period ends with one of the noble gases. These are at the low points of the pattern. And notice a noble gas ends each period in the periodic table. And lithium and the other metals in the column under it begin each period in the table. In the graph, each periodic rise in melting point begins with one of the metals in the lithium column. This same sort of periodicity shows up in the graphs of other properties of the elements when they're arranged as they are in the periodic table. Density, the mass per unit volume. Ionization potential, the energy required to remove an atom's outermost electron. But not only do the ionization potentials of helium, neon, argon, and the other noble gases have the same relative positions in the graph as they do in the periodic table, but so do the other elements in between, from fluorine and chlorine to lithium, sodium, and potassium. And in fact, if we simply laid out the elements from helium to potassium in order of atomic number on a strip of paper and wrapped it around a cylinder so that the noble gases fell in the same vertical column, we'd get the same correlations we saw on the graph. But these groups of elements share many more similarities than relative ionization potential. Take lithium, sodium, and potassium. All are soft metals with low densities and low melting and boiling points for metals. All are extremely reactive chemicals, even reacting violently with water. None of these elements is ever found pure in nature. Fluorine and chlorine, both gases at room temperature, are highly reactive nonmetals. Fluorine, like chlorine, is never found free in nature, only in compounds. And of course, helium, neon, and argon are all highly unreactive gases and always found in their pure form in nature. Of course, what this spiral arrangement leads us to, by snipping the strip apart after helium, neon, and argon, is the periodic table, in which most of the elements that fall in the same vertical columns are so similar that they're thought of as families. The alkali metals, the halogens, the noble gases. Hydrogen is a problem. As element number 1, it's usually placed here, but hydrogen's properties are only partly like those of the alkali metals. It also behaves something like the halogens. Usually, hydrogen is thought of as being related to both families and is often found in both places on the table. And so here we have the modern periodic table, based on what is probably the most influential single work in the history of chemistry. Man-made element number 101, Mendelevium, honors the Russian chemist Dmitry Mendeleev. who in 1869, drawing on the work of many before him, put together the beginnings of our modern arrangement of all the known elements based on their periodic properties. No one had done it before, and no one knew why the table should work until scientists developed a new model of the atom that revealed an even more fundamental periodic variation in matter. We start with the nucleus of an atom. But keep in mind, while we visualize an atom, that there is no way to show relative sizes correctly. If the nucleus were the size of a pea, about a centimeter in diameter, and in the middle of a soccer field, the outer limits of the atom itself would pass through the goalposts. The diameter of an average atom is actually some 10,000 times larger than the diameter of its nucleus. Keep that in mind as we start with the nucleus of an atom and visualize our model, with sizes of the various parts out of proportion to each other. The number of protons in the nucleus, the atomic number of that element, is balanced by the same number of electrons outside the nucleus. We think of these electrons not like planets in orbits, but in terms of certain regions where electrons are most likely to be found. They're more accurately called shells or energy levels. To identify them, energy levels are numbered from the nucleus out. The levels have sublevels. The first has only a single sublevel. Level 2 has 2 sublevels. Level 3 has 3 sublevels. Level 4 has 4 sublevels, and so on. Each new level has one more possible sublevel. Sublevels are given letter names. The first sublevel of each level is named S. The next is P. The third is D. The fourth is F. Sublevels have different capacities for electrons. We show these capacities by counting orbitals. There's one spherically shaped orbital for any S sublevel. It has a capacity for 2 electrons. 2 is the maximum number of electrons any orbital can accommodate. The orbital is simply a region where the electrons are most likely to be found. There are 3 dumbbell-shaped p orbitals. Each one can accommodate 2 electrons. And collectively, the p orbitals, when filled, actually form a spherical region of even density. There are 5 d orbitals of varying shapes and spatial orientations. Each one, again, can accommodate 2 electrons, giving the 5 d orbitals a capacity of 10 electrons. When filled, they also form a spherical region of even electron density. Let's see what we have so far in our atom model. Each S sublevel has 1 orbital and can hold 2 electrons. Each P sublevel has 3 orbitals and can hold 6 electrons. Each D sublevel has 5 orbitals and can hold 10 electrons. This is how the first 3 energy levels are arranged. The 4th energy level also has an F sublevel of 7 orbitals with a total capacity of 14 electrons. The number of the energy level is the same as the number of sublevels it has. And the number of orbitals in each sublevel starts with 1 and then increases by 2. 1, 3, 5, 7, and so on, with 2 electrons possible in each orbital. Now, how does this model explain the workings of the periodic table? Remember, the elements in the table are arranged in order of atomic number. Consider hydrogen. Because hydrogen is element number 1, its atomic number is 1, so it has 1 proton in its nucleus. And that means it has 1 electron to balance that charge. Now, according to our atom model, based on energy levels, electrons begin filling in the lowest available energy level of an atom. And so hydrogen, with just one electron, has it in the single orbital of the first level. Helium is element number 2, with 2 protons, and so it has one more electron than hydrogen does to balance its charge. And there's room for that second electron in the orbital of the first level. With helium, that level is filled. Any more electrons must go into the next level. And now notice the periodic table. Just 2 elements are in the first period, filling it just as 2 electrons fill the first energy level. The first element of the second period is lithium, element number 3. 2 electrons are in the first level, and 1 is in the S sublevel of the second energy level. Now, each element in sequence in the second period has 1 more proton in the nucleus, and therefore 1 more electron in the sublevels of the second energy level, until neon, with 8. And now, the second energy level is filled. Additional electrons must go into the third energy level. And once again, a new period in the table begins. Each time another proton is added to the nucleus, another electron is needed to balance that charge. Sodium is element number 11. 10 of its 11 electrons are in the first 2 levels of its atom, 2 in the first level, 8 in the second level. The 11th electron begins filling the third level. This means sodium has 1 electron in its outermost level, just as lithium above it, and hydrogen above lithium does. Now each element in sequence after sodium has 1 more outermost electron, each in the third level. Magnesium has 2, just like beryllium. Aluminum has 3, just like boron, and so on through the period. The orbitals of the D sublevel are next, but electrons always fill the lowest energy level available, and this D sublevel of the third level is not the lowest. So the next electron in an atom goes into the S sublevel of the fourth level. And a new period begins on the table, the fourth, with potassium, which has 19 protons. And as protons are added, additional electrons are added to balance the charge. Potassium has 1 electron in that S sublevel of the fourth level. Calcium has 2. Again, 1 and 2 outermost electrons, the same as in the pairs of elements above them. And now that the S sublevel of the fourth level is filled at calcium, the D sublevel of the third level begins filling in. With its 5 orbitals, it has a capacity for 10 electrons. And the next 10 elements in the periodic table are the result of this sublevel being filled, 1 electron at a time. And now the p orbitals of the fourth level can be filled. And as each electron is added, each of the next 6 elements in the periodic table is formed, each with the same outer electronic configuration as the 6 elements in the period above them. Now, so far, we've gone through about a third of the elements in the periodic table. Remember, Mendeleev arranged the table so that the elements with similar chemical properties fell in the same vertical columns. And based on our model, elements in the same vertical columns have the same number of electrons in their outermost energy levels. These electrons primarily determine chemical activity. Because the arrangement of these electrons recur periodically, the properties they produce recur in the same periods. And what we have demonstrated for the first 4 periods of the table holds for all 7 of them. Elements with the same number of outermost electrons fall in the same vertical columns, and all have similar properties. Now the atom model explains not only why there are certain families of elements, but why certain trends are seen in the table. Why, for instance, do the elements in the table become less metallic across any one period? Because metallic properties depend on the number of electrons in the outer shell. Sodium, in the first column, has 1. As the number of the outermost electrons increases across the period, the metallic properties decrease. After aluminum, the metalloid silicon begins the change into the non-metals phosphorus, sulfur, and chlorine, and finally argon. And then 1 electron appears in the next level, and we have a metal again, potassium. The periodic repetition of the properties of the elements, melting point, density, ionization potential, all the physical and chemical properties can be explained by this model that demonstrates the periodic nature of the structure of the atom. And this model explains why Mendeleev's periodic table worked. Like a map of a complex region, it summarized and organized a tremendous amount of information. Also, like a map, it offered guidance into unknown areas. Mendeleev was the first to use it in this way. As he worked out his table, there was a blank space below silicon. Trusting the map-like character of the table, he predicted that an element should exist to fill this space. He named it ecosilicon. Mendeleev based his table on the related properties of the elements. So he reviewed the trend in the properties of elements in the group containing silicon and calculated intermediate values for ecosilicon's properties. He predicted that ecosilicon's density would be about 5.5 grams per cubic centimeter. He also predicted that it would form a compound with 4 atoms of chlorine, and that this compound would boil at about 100 degrees Celsius. A few years later, the element was discovered and officially named germanium. Germanium's density is 5.36 grams per cubic centimeter. Germanium forms GeCl4, and this compound boils at 83 degrees Celsius. Mendeleev's predictions were remarkably close for an unknown element. In naming element 101 for Mendeleev, the scientific world underscored the great significance of his work. Mendeleev's periodic table, the basis of our modern table of the elements, provided a remarkable summation of information. It led us to a far more profound understanding of the nature of our world than we had ever had before. The Earth is a cosmic laboratory, shaped and reshaped by countless chemical reactions. Certain fundamental factors influence these reactions and the rates at which they take place. Exposure to air and water slowly causes iron to rust. When iron rusts, it reacts chemically with oxygen. It's a slow, almost imperceptible reaction. We can produce the same reaction in a laboratory. Instead of an old wagon, we'll use steel wool, which is mostly iron. Instead of air, which is only 20% oxygen, we'll use pure oxygen. Here's how iron can react with oxygen, quite a bit more violently than it normally does in nature. Some of the wood in a match burns, reacting with oxygen in the air, and in a few seconds, the charred part is mostly carbon. But for a prehistoric forest, buried by vast cataclysmic changes in the earth, it will take 1,000,000 years for its wood to undergo similar chemical reactions that also turn the wood to carbon in the form of coal. Reactions take place at different rates. Into 2 beakers, we pour dilute hydrochloric acid. A sample of magnesium on the left and iron on the right will be dropped into the acid. The metal magnesium reacts rapidly and violently. But in the other beaker, the metal iron rests on the bottom, reacting slowly. Once again illustrating a basic idea. Different reactions take place at different rates. But why? The answer relates to chemical bonds. In reactions, chemical bonds are involved, some breaking, others forming. The factors that control the rates at which these changes take place are the factors that control rate of reaction. At room temperature, there's almost no reaction between methane gas and oxygen. The heat of a flame is required to start the reaction. But at the same temperature, nitric oxide, NO, one of the products in automobile exhaust gases, oxidizes moderately fast into brownish nitrogen dioxide, NO2. This is a reaction involved in the production of smog. Here are the 2 reactions. One, extremely slow. One, moderately fast. The difference in reaction rates lies in the difference in the nature of the reactants, methane and nitric oxide, which leads us to our first point. The rate of reaction is affected by the nature of the reactants. In the moderately fast reaction between nitric oxide and oxygen, only a few relatively weak bonds have to break. In the extremely slow room temperature reaction between methane and oxygen, many strong bonds have to break. Generally, the stronger the bonds, the slower a reaction rate will be. And the strength and number of those bonds depend on the nature of the reactants, one of the several factors that influence reaction rates. You don't usually think as an explosive, but when wheat or other grain is loaded into grain elevators for storage, dust from the grain fills the air inside the elevator. Just a tiny spark or flame, and this mixture of wheat dust and oxygen in the air can react extremely rapidly and explode violently. And yet, when the elevator is packed solid with grain, there's very little danger of explosion. Many solid substances that react slowly in large pieces react rapidly in the form of dust. Coal burns slowly, but coal dust burns explosively, which leads us to a second factor affecting reaction rates: the surface area of solids. Coal is essentially carbon. When it burns, atoms of oxygen react with exposed atoms of carbon. Only those on the surface exposed to oxygen can react. If we cut the piece of coal in half, more area is exposed to the oxygen, so more reactions can take place at the same time. The rate of reaction is going up. Each time more surface area is exposed, the reaction rate increases, as long as enough oxygen is available. Eventually, if the lump of coal is converted to tiny dust particles, the surface area available for reaction with oxygen is increased tremendously, and the reaction rate is so rapid that an explosion results. Surface area is significant when solids, or substances in different phases, are involved in a chemical reaction. To illustrate another factor, we can let a dilute potassium iodate solution react with an acidified sodium sulfite solution that contains a starch indicator. The solution will turn blue when the reaction, which involves several steps, nears completion. The solution turns blue in about 35 seconds. Now, using a solution of potassium iodate that's 10 times as concentrated, we allow them to react again. Now the solution turns blue in only 20 seconds rather than 35. Illustrating this point, rate of reaction is also affected by the concentration of the reactants. Electrolytically, we can break apart the compound water into its constituent elements, hydrogen and oxygen. Once hydrogen gas forms, we can easily recombine it with oxygen in the air. It seems like a rapid reaction, but compare that with this. In some liquid-fueled rockets, liquid hydrogen, much more highly concentrated than the gas, reacts with liquid oxygen. The reaction proceeds at a very rapid rate, almost a controlled explosion. Concentration clearly makes a difference in the rate of reaction, and so does the temperature of the reactants. In the frigid ice fields of the polar regions, there's little decay. Food left behind by polar scientists has remained fresh and edible for 50 years or more. But in the tropics, the chemical reactions of decay proceed at a rapid rate. In tropical heat, foods spoil quickly and easily. Every time a fuel is ignited, it's a demonstration that reactions that may take place extremely slowly at room temperature can be sped up considerably when the reactants are heated. The fact that concentration and temperature of reactants both affect reaction rate can be explained by the same concept: collision theory. According to this theory, reactions occur when colliding particles momentarily form an activated complex. Then the complex falls apart into new compounds. In any particular reaction, the more particles that are crowded into a given space, the more collisions will take place. This is what happens when we increase the concentration of reactants. A greater concentration leads to more collisions, and more collisions in a given unit of time make a faster rate of reaction. Collision theory also helps us understand how temperature affects reaction rate. When a reaction gets hotter, on the average, its particles move faster, collide more frequently, and with more energy. Now, many collisions are duds. They don't have enough energy to form activated complexes. Or if they do, the complexes fall back into their original configurations. Collision theory suggests that an increase in temperature reduces the number of duds in a reaction. Here's how. Let's think of a reaction in terms of a hill and a ball. In order for the ball to roll over the hill, it must have a certain amount of energy. We can think of this as the activation energy for a reaction. If colliding particles have enough energy, activation energy is achieved and a reaction takes place. For every reaction, there's a particular minimum activation energy needed before a collision can be successful. If particles collide too gently, or with an orientation that requires more than the minimum energy for the reaction to occur, activation energy might not be achieved, and no reaction take place. An increase in temperature increases the energy of the collisions. A larger percentage of the collisions can be effective. Besides the nature of the reactants, surface area, concentration, and temperature, there's one more important factor that can influence a reaction's rate. In a hydrogen peroxide solution, the hydrogen peroxide slowly decomposes into water and oxygen. Occasionally, a tiny bubble of oxygen forms. Now, we warm the solution. As we expect, this increases the reaction's rate. Now watch what happens when we add a solution that contains iodide ions. The reaction rate changes significantly. The iodide ions act as catalysts. Catalysts are substances that can have profound effects on the rate of reaction. They work by providing what is called an alternate reaction path. For example, iodide ions change the reaction path by which hydrogen peroxide decays into water and oxygen. Instead of the slow steps by which hydrogen peroxide, H2O2, normally breaks down into water and oxygen gas, the catalyst triggers a new set of steps, which happen to go very quickly, one after the other. The products of these reactions are water, oxygen, and exactly the same amount of catalyst as we added at the beginning. The catalyst appears unchanged, but it's made the reaction's product form at a faster rate. To understand how, think of a reaction path as a route over a mountain pass. It takes a certain amount of time and energy, activation energy, to get up to the top of the pass. A catalyst provides an alternate reaction path, a different set of steps involved, a sort of tunnel through the mountain that's not as high a climb, that's easier to travel, and that requires less activation energy. Different catalysts affect reactions in different ways. For example, it's very difficult to make sugar actually burn. Heating it will turn it brown and eventually char it. But oxidation will not continue without an outside supply of heat. But with the proper catalyst, sugar will combine with oxygen so fast that it supports a visible flame. Inside our bodies, we also oxidize sugar for nourishment and for energy. But we need to burn it more slowly. In our bodies, catalysts called enzymes are at work. These substances also let sugar burn, but along slow, complicated reaction paths that release energy at a slow, steady rate. In most living organisms, this slow oxidation takes place in the mitochondria of their cells during the process of cellular respiration. Nerve impulses stimulate the production of a chemical at the ends of a nerve cell. The chemicals, neurohormones, transfer the impulse to a neighboring nerve cell. Then enzymes are released that destroy the hormone in an extremely rapid reaction, making the nerve cell ready to accept another message in a fraction of a second. So far, we've considered reactions as if they only went one way, reactants turning into products. But any reaction is really a two-way process. For example, when potassium bromide and chlorine gas are combined, some of their particles collide, and some of these collisions have enough energy to result in a reaction. In this case, the result is the formation of potassium chloride and brown-colored bromine gas. But at the same time that the potassium bromide and chlorine are reacting, increasing numbers of bromine gas molecules and chloride ions react in the opposite direction. Eventually, the forward and backward rates strike a balance. This is the condition that chemists call equilibrium. When a reaction has reached equilibrium, it may seem as if the reaction has stopped, but it hasn't. Both reactions are still running along, but balancing each other. We can upset that equilibrium in a number of ways. One is by increasing the amount of the original reacting substances. Equilibrium can also be upset by changes in temperature. Here, some molecules of colorless dinitrogen tetroxide, N2O4, are breaking down into brown nitrogen dioxide, NO2, while some NO2 molecules are reforming into N2O4. N2O4 was one of the chemicals used in the reaction that propelled the Lunar Excursion Module off the surface of the Moon into orbit. And nitrogen dioxide, you know, is a constituent of smog. Now these gases are at equilibrium. What will happen in a moment, as we heat these gases, relates to a special characteristic of chemical equilibrium. In every pair of reactions, one reaction is always exothermic. That means that it gives off energy, usually as heat, but sometimes as both heat and light. The other reaction is always endothermic. It has to absorb energy as it proceeds. In the equilibrium we're watching, the formation of N2O4 from NO2 is exothermic, energy releasing, and the opposite reaction is equally endothermic, energy absorbing. When this mixture is heated, the rise in temperature gives a special boost to the endothermic reaction, the breakdown of N2O4 into the brown NO2. Of course, when we cool the mixture, the opposite happens. Now, more colorless N2O4 begins forming, and the gas in our vessel turns pale. In general, adding heat tends to shift the equilibrium in the direction of the endothermic reaction. The nature of the reactants, the surface area, concentration, temperature, catalysts, these factors all affect the rate of reaction. We can see most of these factors at work in a large industrial process. This plant manufactures ammonia by the Haber process. The Haber process depends on a simple chemical equilibrium between nitrogen, hydrogen, and ammonia. Nearly 80% of the air is nitrogen gas, relatively inert at low temperatures. In nature, lightning can provide the energy that allows nitrogen to combine with hydrogen from water molecules and form ammonia. This is a fast, but not very controllable reaction. To be practical, an industrial process must be designed to operate as quickly as possible, but still at a rate that remains controllable. The Haber process was shaped to accommodate the properties of hydrogen, nitrogen, and ammonia. Hydrogen gas and nitrogen gas are piped into the system toward a main reaction chamber. Here, the Haber process increases concentration by greatly compressing the gases. As the gas's concentration increases, the reaction grows more productive. The Haber process also uses increased temperature. This speeds up both the forward and backward reactions. But unfortunately, the reverse reaction is endothermic. Too much heat will break down the ammonia faster than it forms. So chemists compromise by using an intermediate temperature, about 500 degrees Celsius, warm enough to hurry the reaction, but not so hot that it seriously reduces the amount of product formed. Within the reaction chamber, the Haber process also uses catalysts, mostly iron, iron oxide, and potassium aluminate. Since they change the pathway, but not the initial reactants or the final product, catalysts do not change the reaction's equilibrium. But they do speed up the rate at which the reaction reaches equilibrium, saving considerable operating costs. Most of the ammonia produced by this method will be used for fertilizers or in the production of synthetic fertilizers. With its additional uses in refrigeration and in the chemical industry, ammonia is one of our most important compounds. The manufacture of ammonia is just one of thousands of processes that depend on reaction rates and our ability to control the factors that influence them. The nature of the reactants, the surface area of solids, the concentration of the reactants, the temperature of the reactants, and catalysts. These chemical processes are important not only in the industrial world, but also in the world of nature itself, where chemical reactions have been going on since the Earth was formed.